November 1944. Tachikawa Air Arsenal, near Tokyo. A crowd of Japanese aviation engineers stood in stunned silence, staring at the largest aircraft any of them had ever seen. It dwarfed everything around it. Its wingspan stretched wider than 3 Japanese bombers parked wingtip to wingtip. Its 4 massive engines looked like they belonged on a battleship, not an airplane. This was a Boeing B-29 Superfortress. The aircraft that had been bombing Japan's cities and factories with seeming impunity for months. And now, through extraordinary circumstances, Japanese engineers had one to examine up close. Colonel Takeo Yamashita, Chief of Aircraft Evaluation for the Imperial Japanese Army Air Force, walked slowly around the massive bomber. His face showed no emotion, but his mind was racing. This aircraft represented everything Japan feared about American technological capability. "How many crew does it carry?" asked a young engineer standing nearby. 11 men, Yamashita replied quietly. "And they fly at altitudes our fighters struggle to reach, drop tons of bombs with precision we cannot match, and return to bases we cannot attack. This aircraft, more than any other weapon in the American arsenal, may decide the war's outcome." The B-29 before them had not been shot down. It had force-landed in Soviet territory after a raid on Manchuria. Through diplomatic channels and intelligence operations, components and technical data had made their way to Japan. It wasn't a complete aircraft, but it was enough to conduct a thorough evaluation. Over the next 6 weeks, Japanese engineers would disassemble, measure, analyze, and test every system they could access. They would study the engines, the pressurization system, the remote-controlled gun turrets, the radar bombing equipment, and the sophisticated manufacturing techniques visible in every component. And with each discovery, the same terrible realization would grow stronger. Japan had no answer to this aircraft. Not now. Possibly not ever. This is not a story about a battle or a campaign. This is a story about the moment when Japanese aviation experts confronted the true scale of the technological gap between Japan and America. When they understood that the B-29 wasn't just a better bomber. It was a quantum leap in aviation technology that Japan's industry simply could not replicate. The B-29 Superfortress was designed to do what seemed impossible: fly higher than enemy fighters could effectively intercept, carry massive bomb loads over thousands of miles, defend itself with sophisticated weapon systems, and operate in comfort at altitudes where the air was too thin to breathe. And it did all of this while being produced in quantities that seemed absurd. By late 1944, America was building dozens of B-29s every month. Each one cost approximately $600,000 and required over 55,000 man-hours to construct. Yet they rolled off assembly lines in Kansas, Georgia, and Washington state in a steady stream. Japan's aviation industry could barely keep up with replacing combat losses of much simpler fighters. The idea of mass-producing aircraft as complex as the B-29 was beyond Japanese industrial capacity entirely. Colonel Yamashita knew this. His engineers knew this. But examining the B-29 would force them to document exactly how far behind Japan had fallen and why catching up was impossible. The B-29 raids had begun in June 1944, striking from bases in China and later from newly captured islands in the Marianas. Japanese cities burned. Factories were destroyed. And Japanese fighters, even when they reached the high-flying superfortresses, found them nearly impossible to shoot down. The B-29's defensive armament was devastating. Its speed at altitude was higher than most Japanese fighters could achieve. And even when Japanese pilots scored hits, the massive bomber could absorb tremendous damage and keep flying. Some Japanese commanders had convinced themselves that American bombers were poorly built, that they lacked the warrior spirit of Japanese aircraft, that they were just another example of American industrial quantity over Japanese quality. The engineers at Tachikawa were about to prove those commanders catastrophically wrong. This B-29 was built to a standard of engineering sophistication that Japan could not match. It incorporated technologies Japan didn't possess. It was manufactured using processes Japanese industry couldn't replicate. And most crushing of all, it was just one of thousands. For the next 6 weeks, Japanese engineers would document these realities in painful detail. They would measure, photograph, analyze, and report. And their conclusions would help explain why the air war over Japan was already lost. The B-29 Superfortress wasn't just bombing Japan's cities. It was demonstrating America's total dominance in aviation technology, manufacturing capability, and strategic air power. And there was nothing Japan could do to stop it. The evaluation was about to begin. And every discovery would make Japan's strategic situation look more hopeless. The story of how Japan obtained access to a B-29 Superfortress is complicated, involving multiple aircraft, espionage, and an unlikely Soviet role. The first B-29 to fall into unfriendly hands was actually captured by the Soviet Union, not Japan. On July 29, 1944, a B-29 named Ramp Tramp from the 58th Bombardment Wing was damaged during a raid on the Showa steelworks in Manchuria. With fuel running low and systems failing, the pilot, Captain Howard Jarrell, made the decision to divert to Soviet territory and attempt an emergency landing. The Soviets were not at war with Japan at this point, maintaining an uneasy neutrality. When Ramp Tramp landed at a Soviet airfield near Vladivostok, the Soviets interned the crew and impounded the aircraft. Over the following months, 3 more damaged B-29s would make emergency landings in Soviet territory under similar circumstances. Stalin, always interested in advanced military technology, ordered the B-29s to be thoroughly studied. Soviet engineers began detailed examination and measurement of the aircraft, eventually leading to the creation of the Tupolev Tu-4, a nearly exact copy of the Superfortress. But the Soviets were not the only ones interested in the B-29. Japanese intelligence had been desperately seeking information about the new American bomber since the raids began. Through intelligence networks in Manchuria and contacts with Soviet personnel, the Japanese managed to obtain photographs, technical measurements, and eventually, actual components from the interned aircraft. Additionally, Japanese forces had recovered wreckage from B-29s that had been shot down or crashed in the Pacific Theater. These wrecks were carefully collected and shipped to Japan for analysis. While no single crashed B-29 provided a complete aircraft, Japanese engineers were able to assemble enough components and data to conduct a comprehensive technical evaluation. The most significant intelligence coup came in November 1944, when Japanese agents obtained detailed photographs and measurements of an interned B-29 being studied at a Soviet facility. These images showed the aircraft's interior systems, equipment layout, and construction details with remarkable clarity. Combined with recovered components from crashed aircraft, Japanese engineers at Tachikawa Air Arsenal had enough material to understand the B-29's capabilities, even without having a fully intact, flyable example. The evaluation team assembled at Tachikawa was Japan's best. Colonel Takeo Yamashita led the effort, supported by engineers from Mitsubishi, Nakajima, and Kawasaki, Japan's primary aircraft manufacturers. Specialists in engines, armaments, electronics, and structures were all represented. Their mission was urgent. The B-29 raids were devastating Japanese industry and urban centers. Air defenses were proving inadequate. Japanese fighters struggled to intercept the high-flying bombers. When they did reach the B-29s, they found the superfortresses difficult to shoot down and heavily defended. High Command needed to know, what made the B-29 so effective? What technologies enabled its performance? Could Japan develop countermeasures? Could Japanese industry produce anything comparable? The answers to these questions would determine Japan's defensive strategy for the remainder of the war. The engineers began their work in late November 1944. They had access to the forward fuselage section of a crashed B-29 recovered from the ocean near Iwo Jima, including the cockpit and nose compartment. They had multiple engine components from various wrecks. They had landing gear assemblies, pieces of wing structure, sections of the tail, and most valuably, portions of the defensive armament system including gun turrets and fire control equipment. Additionally, they had hundreds of photographs from the Soviet interned aircraft, technical manuals that had been captured or obtained through intelligence channels, and reports from Japanese pilots who had engaged B-29s in combat. It wasn't perfect. They couldn't test-fly the aircraft or fully evaluate its flight characteristics. But they had enough to understand the B-29 systems, construction, and capabilities. The evaluation would be divided into several focus areas: propulsion systems, pressurization and environmental control, defensive armament, bombing and navigation systems, structures and manufacturing techniques, and overall design philosophy. Each area would reveal capabilities that Japan could not match. On the first day of detailed examination, the engineering team gathered around the forward fuselage section. Even in pieces, the B-29's size was imposing. The cockpit area alone was larger than the entire crew compartment of Japanese bombers. Before we begin detailed analysis, Colonel Yamashita announced, "I want first impressions. What strikes you immediately about this aircraft?" The answers came quickly. The precision of construction, the quality of materials, the sophistication of systems integration, the attention to crew comfort and safety, the sheer scale of everything. One engineer summed it up: "This is not an evolutionary improvement over existing bombers. This is a completely new category of aircraft. It's as if we're comparing a modern automobile to an ox cart. The fundamental approach is different." Yamashita nodded grimly. "Then let's document exactly how different it is. Begin with the engines." The evaluation team moved to the right. R-3350 engine components they had recovered. These massive radial engines were the heart of the B-29's performance. And examining them would be the first of many shocking revelations. Within hours, Japanese engineers would understand why their fighters couldn't catch the B-29 at altitude. Why the bomber could fly missions of over 3,000 miles. Why it could carry 10 tons of bombs and still maintain high speed. The answers all started with 4 engines producing power levels Japanese aviation had never achieved. The B-29 evaluation had officially begun. And every discovery would make Japan's situation look more desperate. The first thing that overwhelmed Japanese engineers was the sheer physical size of the B-29 Superfortress. Colonel Yamashita had ordered precise measurements of every component available, and as the data came in, the numbers seemed almost impossible. Wingspan, 141 feet, 3 inches. The Japanese G-4M Betty bomber, one of their largest aircraft, had a wingspan of 82 feet. The B-29's wings were nearly twice as wide. Length, 99 feet. Weight, 140,000 pounds maximum takeoff weight. By comparison, the Betty weighed 33,000 pounds fully loaded. "This aircraft weighs more than 4 of our heavy bombers combined," noted an engineer from Mitsubishi. "And it carries a crew of 11 men in what appears to be considerable comfort." The engineering team examined the recovered cockpit section closely. The pilot and co-pilot sat side by side in adjustable seats with cushioning. The instrument panel was enormous, filled with dozens of gauges, indicators, and controls. Everything was clearly labeled. The layout was logical and ergonomic. Behind the pilots, the flight engineer had his own station with a complete set of engine instruments, fuel management controls, and systems monitors. This was a dedicated crew position just for managing the aircraft's complex systems. Japanese bombers had no such position. Pilots managed engines while flying. There was no redundancy, no specialization of crew roles to this degree. The cockpit windows were thick, optically clear glass. The visibility was excellent in all directions. Overhead, there were additional windows for astronomical navigation. The attention to pilot needs was evident in every detail. "Look at this," called out one engineer, examining the cockpit environmental controls. "There are vents for heated air. Temperature controls. The Americans are heating their cockpit at altitude." Another engineer found what appeared to be oxygen system components. But these weren't the simple oxygen bottles and masks Japanese aircraft used. This was a sophisticated pressurized system with regulators, flow meters, and redundant supplies. The physical comfort provisions astounded the Japanese team. American bomber crews had padded seats, insulated flight suits, heated gloves, and boots. There were provisions for hot food and coffee during long missions. Japanese bomber crews sat on hard benches in unheated, unpressurized aircraft. They endured cold that could cause frostbite at high altitude. Many suffered from hypoxia due to inadequate oxygen systems. Physical endurance was considered part of a warrior's duty. The Americans designed their aircraft around crew comfort, Yamashita observed. We design our aircraft for maximum performance, and crews must endure whatever conditions result. This is a fundamental philosophical difference. The structural examination revealed construction techniques that impressed even skeptical Japanese engineers. The B-29 skin was formed from aluminum alloy sheets of consistent, high quality. The riveting was precise and uniform. The tolerances were tight throughout. This is mass production at a level we've never achieved, admitted an engineer from Nakajima. Every rivet is placed consistently. Every panel fits precisely. This isn't craftsmanship in the traditional sense. This is industrial precision applied at enormous scale. They examined the wing structure where it attached to the fuselage. The engineering was sophisticated, using massive spars and ribs to support the enormous wingspan. The fuel tanks were integrated into the wing structure, holding thousands of gallons of fuel. The landing gear components they had recovered were massive. The main gear struts were as thick as a man's torso, constructed from high-strength steel alloys. The tires were enormous, designed to support the aircraft's tremendous weight. Even the landing gear represents technology beyond our current capability, noted a structures engineer. The materials, the manufacturing precision, the hydraulic systems, all of it is more advanced than what we're producing. The electrical system components told a similar story. Miles of wiring, all color-coded and organized. Circuit breakers and fuses throughout. Multiple generators providing redundant electrical power. The B-29 had more electrical systems than some Japanese factories. The engineering team found provisions for crew comfort that seemed almost luxurious. There was a relief tube system for crew use on long missions. There were storage compartments for personal items and emergency equipment. There was even a small galley area for preparing hot food. They've designed this aircraft for missions lasting 15 or 16 hours, Yamashita said. Our bombers are designed for missions of perhaps 6 or 7 hours maximum. The operational concept is completely different. The radio and communications equipment was far more sophisticated than Japanese systems. The B-29 carried multiple radio systems for different purposes: long-range communications, inter-crew communication, radio navigation, and equipment for coordinating with other aircraft information. Japanese bombers typically had one radio, if they had working radios at all. Equipment failures were common. Communication between crew members was often by hand signals or shouting over engine noise. After 3 days of initial examination, Colonel Yamashita assembled his team for preliminary observations. Gentlemen, we're seeing an aircraft that represents a completely different approach to bomber design. The Americans have prioritized crew survivability, long-range operations, heavy payload capacity, and high-altitude performance. They've built enormous complexity into every system, but they've also built redundancy and reliability. He paused, looking at the data they'd collected. More concerning is the manufacturing quality. This aircraft was built by workers in American factories, yet the precision and consistency suggest advanced industrial processes we cannot replicate. An engineer raised a troubling question. Colonel, if the Americans can build aircraft this sophisticated in the quantities intelligence suggests, hundreds, possibly thousands, what does that mean for our defensive capabilities? Yamashita's response was blunt. It means we need to understand this aircraft completely. Because if we can't find weaknesses to exploit, our air defenses may be inadequate regardless of how many fighters we produce. The size and sophistication of the B-29 was intimidating. But the engineering team hadn't yet examined the systems that made it truly revolutionary. The pressurization system. The remote-controlled defensive armament. The radar bombing equipment. Those revelations were still to come. And each would be more shocking than the last. On the fourth day of evaluation, Japanese engineers made a discovery that would fundamentally explain why their fighters struggled so desperately to intercept B-29s. A young engineer examining the cockpit section noticed something unusual. The entire forward compartment was sealed. Not just weather-sealed, but hermetically sealed with heavy rubber gaskets, pressure doors, and reinforced bulkheads. "Colonel Yamashita," he called out, "I think this entire compartment is pressurized." The implications took a moment to register. Then the entire engineering team converged on the cockpit section. Pressurization. The ability to maintain sea-level atmospheric pressure inside the aircraft while flying at 30,000 feet or higher. This meant the crew could operate in normal conditions, breathing regular air, working in comfort, while the aircraft flew at altitudes where the outside air was too thin to sustain human life. "This changes everything," Yamashita said quietly. "If the B-29 can operate effectively at altitudes where our fighters struggle, it's not just faster or better armed. It's operating in an environment where we can barely reach it." The engineering team spent the next 2 days examining every aspect of the pressurization system they could access. What they discovered was a masterpiece of engineering that Japan had never even attempted. The B-29 had 3 pressurized compartments: the forward cabin containing the cockpit and bombardier station, the rear cabin for gunners, and a connecting tunnel running through the unpressurized bomb bay. The crew could move between compartments through this tunnel during flight. The system maintained cabin pressure equivalent to 8,000 feet altitude while the aircraft flew at 30,000 feet or higher. This meant the crew experienced comfortable conditions similar to a mild mountain elevation while operating in the stratosphere. To achieve this, the B-29 used engine-driven compressors to force outside air into the sealed compartments. Regulators maintained proper pressure automatically. Outflow valves prevented overpressurization. The entire system was redundant, with backup compressors and manual controls if automatic systems failed. Japanese engineers calculated the pressure differential. The sealed compartments had to withstand roughly 10 pounds per square inch difference between inside and outside pressure. This required reinforced structure throughout the pressurized areas. "The structural engineering required for this is extraordinary," noted a structures specialist. "Every seam must be sealed. Every door must lock with pressure-tight gaskets. The entire fuselage in the pressurized sections must be strengthened to handle the stress." More impressive was that the system worked reliably. Intelligence reports indicated B-29s regularly operated at altitudes above 30,000 feet with no crew issues. American bomber crews wore regular flight suits, not pressure suits. They breathed normally, not through oxygen masks for the entire mission. The tactical implications were devastating for Japanese air defense. Japanese fighters like the Ki-61 and J-2M could reach 30,000 feet, but only barely. At that altitude, they were at the edge of their performance envelope. Engine power was reduced. Controls were mushy. Climb rate was minimal. Pilots suffered from cold and hypoxia despite oxygen systems. The B-29, operating in its pressurized comfort, had full crew effectiveness at the same altitude. Pilots were alert and warm. Bombardiers could work precisely. Gunners could track targets effectively. The aircraft itself performed well because its engines were turbocharged for high-altitude operation. "We're asking our pilots to fight at the edge of what's physically possible," Yamashita said grimly. "The Americans are operating comfortably in the same environment. The performance disadvantage this creates is insurmountable." The engineering team studied the pressurization technology desperately, looking for ways Japan could replicate it. The conclusion was discouraging. The system required advanced compressor technology Japan didn't possess, sophisticated pressure regulation and control systems beyond Japanese manufacturing capability, high-quality seals and gaskets requiring materials Japan couldn't produce consistently, structural engineering and testing that would require years of development. Even if Japan could design a pressurization system, they lacked the industrial capacity to manufacture it in quantity. The B-29's pressurization system alone probably cost more than entire Japanese fighter aircraft. We could perhaps build 1 or 2 pressurized aircraft as experimental prototypes, admitted an engineer from Kawasaki. But producing them in quantities sufficient to matter operationally? Impossible with our current resources and industrial base. The crew comfort advantages were equally telling. At 30,000 feet without pressurization, temperatures outside dropped to 40 or 50 degrees below zero. Japanese bomber crews wore heavy flight suits and still suffered from cold. Frostbite was common. Hypoxia affected judgment and performance. B-29 crews operated in shirt sleeves. The heating system maintained comfortable temperatures throughout the pressurized compartments. Crews remained alert and effective throughout missions lasting 15 hours or more. This is why B-29 bombing accuracy is so high, Yamashita realized. Their bombardiers are working in comfortable conditions with full mental acuity. Our bomber crews are often suffering from cold and oxygen deprivation by the time they reach the target. The pressurization system also explained B-29 survivability. Japanese fighter pilots reported that even when they reached B-29 formations at altitude, they could only make brief attacks before their aircraft's performance degraded. Sustained combat was impossible at 30,000 feet for Japanese fighters. Meanwhile, B-29s could maintain altitude indefinitely. They weren't pushing their performance limits. They were operating well within their designed capabilities. The psychological impact on Japanese pilots was significant. They knew that reaching the B-29s required climbing to altitudes that exhausted them and their aircraft. They knew that even successful attacks often failed to bring down the massive bombers. And they knew the Americans could return day after day with fresh aircraft and crews. One piece of intelligence particularly troubled the evaluation team. American factories were training pilots for B-29s in pressurized trainers. Pilots learned to operate the systems, manage the pressurization, and handle emergencies. This suggested the Americans had fully industrialized advanced technology that Japan treated as experimental. After documenting the pressurization system, Colonel Yamashita added a somber note to his report. The B-29's pressurization capability provides operational advantages we cannot counter with existing Japanese fighters. Intercepting these aircraft at their operational altitude requires Japanese pilots to operate at the extreme edge of human and machine capability. The Americans operate comfortably in the same environment. This asymmetry makes effective air defense extraordinarily difficult. The pressurization system was just one aspect of the B-29's sophistication. But it alone explained why Japanese fighters struggled so desperately to stop the bombing raids. The Americans weren't just flying higher. They were flying in an environment where Japanese aircraft could barely survive, while the B-29 crews operated as if at sea level. It was a technological advantage with no tactical counter. The Wright R-3350 duplex Cyclone engines that powered the B-29 represented a quantum leap in aircraft engine technology that Japanese engineers had never seen before. Each engine produced 2,200 horsepower. The B-29 had 4 of them. Total power output, 8,800 horsepower. For comparison, the Nakajima Hamar engine powering Japan's advanced fighters produced about 1,800 horsepower. Japanese bombers like the G-4M Betty used 2 Mitsubishi Kasei engines producing 1,530 horsepower each, 3,060 horsepower total for the entire aircraft. The B-29 had nearly 3 times the total power of Japan's largest operational bomber. How is this even possible? Asked an engineer from Nakajima, examining the massive engine components they had recovered. An 18-cylinder radial producing this much power reliably? The answer lay in sophisticated engineering and metallurgy beyond Japanese capability. The R-3350 was a twin-row radial engine with 18 cylinders arranged in 2 rows of 9. The cylinders themselves were marvels of precision manufacturing, with advanced cooling fins and internal passages. But the real secret was the turbocharging system. Each engine had two General Electric turbo superchargers that used exhaust gases to compress intake air, maintaining sea-level pressure to the engine even at high altitude. Japanese engineers had attempted turbocharger development but never achieved reliable, production-ready systems. The metallurgy required for turbine wheels operating in extreme heat was beyond Japanese industrial capability. The precision manufacturing tolerances were too tight for Japanese factories to maintain consistently. The Americans have industrialized technology we can barely produce in laboratory conditions, Yamashita observed. These turbo superchargers are manufactured in quantity, installed in thousands of engines, and operate reliably under combat conditions. The fuel system for the four engines was equally sophisticated. The B-29 carried over 9,000 gallons of fuel in multiple wing tanks with complex fuel management systems. Fuel pumps, valves, and transfer systems ensured proper fuel flow to all four engines under all conditions. The fuel capacity alone exceeded the total weight of many Japanese fighters. The B-29 could fly over 3,200 miles with a full bomb load, farther than the distance from the Marianas to Tokyo and back with combat reserves. Japanese bombers had ranges of 1,500 to 2,000 miles maximum, and that was without carrying heavy bomb loads. The strategic implications were clear. B-29s based in the Marianas could strike anywhere in Japan, while Japanese bombers couldn't reach American bases. The cooling system for the engines impressed the evaluation team significantly. Each R-3350 had cowl flaps that could be adjusted in flight to manage engine temperature. The oil cooling system used separate radiators with controllable airflow. The engine management systems are sophisticated enough that they require a dedicated flight engineer position, noted an engineer examining the recovered instruments. One crew member's entire job is monitoring and managing four engines. We don't have that level of specialization in our bombers. The propellers were another revelation. Each engine drove a massive four-blade Hamilton Standard constant-speed propeller, 16.5 feet in diameter. The propeller pitch was controlled electrically and automatically adjusted for optimal efficiency at different power settings and altitudes. Japanese propellers used simpler two-blade or three-blade designs with manual pitch control. Pilots had to adjust propeller settings based on experience and judgment. The American system was automated, reducing pilot workload and optimizing performance. The reliability of the R-3350 engines, despite their complexity, was documented in intelligence reports. B-29s regularly flew 15-hour missions without engine failures. Maintenance intervals were long. Engine life between overhauls exceeded what Japanese engines achieved. They've achieved reliability through precision manufacturing and high-quality materials, explained a metallurgy specialist examining engine components. Every part is made to exact specifications. The alloys used in critical components are superior to what we can produce. The result is complex engines that are also reliable. The power-to-weight ratio of the complete B-29 system was impressive. Despite weighing 140,000 pounds fully loaded, the aircraft could cruise at over 220 miles per hour and reach altitudes above 30,000 feet. The enormous power output from four engines made this performance possible. Japanese engineers calculated that to achieve similar performance, they would need to develop engines producing at least 2,000 horsepower each with reliable turbocharging. Current Japanese engine development programs were targeting 1,800 to 2,000 horsepower for next-generation fighters, not bombers. We're years behind in engine technology, Yamashita concluded. And the Americans are already producing these advanced engines in quantity. They're not experimental. They're operational and reliable. The fuel consumption, while high by Japanese standards, was actually efficient given the B-29's size and performance. At cruise power, the four engines consumed approximately 900 gallons per hour total. With 9,000 gallons capacity, this gave the aircraft 10 hours of flight time, sufficient for the Marianas to Japan and back mission profile. The evaluation team's engine assessment concluded with a sobering summary. The Wright R-3350 engines represent engine technology at least 5 years more advanced than current Japanese capabilities. The turbocharging systems, in particular, provide high-altitude performance we cannot match. Combined with the B-29's pressurization system, these engines enable operational capabilities beyond the reach of Japanese interceptors. The power revelation explained everything. Why B-29s could fly so high, so far, and so fast. Why they could carry such heavy bomb loads. Why Japanese fighters struggled to catch them even in dives. The answer was brute force power, multiplied by sophisticated engineering, and backed by industrial capacity to produce thousands of these complex engines reliably. Japan had nothing that could compete. And developing equivalent capability would take years Japan didn't have. When Japanese engineers examined the B-29's defensive armament system, they encountered technology that seemed almost like science fiction. The recovered components included portions of a remote-controlled gun turret and elements of the central fire control system. What they revealed left the evaluation team stunned. In conventional bombers, including all Japanese designs, gunners sat directly at their guns. They physically aimed the weapons, compensated for aircraft motion, estimated lead for moving targets, and fired manually. It was direct, mechanical, and required the gunner to be exposed at the gun position. The B-29 was completely different. Gunners sat at sighting stations inside the pressurized compartments, looking through optical sights. The guns themselves were mounted in remote turrets on the aircraft's exterior. The connection between gunner and gun was electronic. The gunner doesn't touch the gun, an engineer said, examining the system in disbelief. He manipulates controls at his station, and electric motors move the turret and guns in response. This is remote control applied to weapon systems. The sophistication went far deeper. The B-29's fire control system used a General Electric central fire control computer that coordinated all defensive guns. This analog computer calculated lead angles, adjusted for range, altitude, temperature, and aircraft speed, then provided corrected aiming to the gunners. The system integrated data from multiple gunners simultaneously. If one gunner had a better shot at an attacking fighter, the computer could automatically direct multiple turrets to his target. 4 or 5 gun turrets could be firing at a single attacker, all coordinated electronically. Japanese engineers had never seen anything remotely comparable. The closest analog in Japanese experience was simple mechanical linkages for manually aimed weapons. Electronic fire control computing was beyond Japanese technology entirely. The B-29 carried 12.50 caliber Browning machine guns in 5 turrets, 2 on top of the fuselage, 2 on the bottom, and 1 in the tail. Additionally, some variants carried a 20 mm cannon in the tail for additional defensive firepower against attackers approaching from behind. The top forward turret had 4 guns. The top rear turret had 2 guns. The 2 lower turrets had 2 guns each. The tail position had 2 guns and possibly the cannon. This created overlapping fields of fire covering every approach angle. An attacking fighter faces multiple guns tracking it simultaneously, Yamashita noted. And those guns are aimed by a computer system that calculates lead automatically. The defensive firepower is coordinated and concentrated in ways our aircraft can never achieve. The gunner positions inside the pressurized compartments meant defensive crews operated in comfort at high altitude. They weren't exposed to cold, wind, or thin air. They could see clearly through optical sights. Their judgment wasn't impaired by hypoxia or cold. Japanese bomber gunners sat at exposed positions, manually operating weapons while enduring temperatures 50 degrees below zero at altitude. The environmental stress alone degraded their effectiveness significantly. The remote turret system also provided better fields of fire. Because the turrets were streamlined and mounted on the aircraft exterior, they had wider traverse and elevation ranges than manually operated guns protruding from the fuselage. The ammunition capacity was staggering. Each .50 caliber gun had approximately 500 rounds. 12 guns meant 6,000 rounds of defensive ammunition. Japanese bombers typically carried a few hundred rounds per gun, and gunners had to conserve ammunition carefully. B-29 gunners could fire sustained bursts at attacking fighters without worrying about running out of ammunition quickly. Intelligence reports indicated B-29s sometimes fired thousands of rounds during missions, something Japanese bombers could never sustain. The electrical and mechanical complexity of the system was daunting. Miles of electrical wiring connected sighting stations to turrets. Electric motors drove the turret traverse and gun elevation. The central computer required electrical power and sophisticated electronics. This system probably requires as much electrical power as our entire bomber, an electrical engineer observed. And it's reliable enough to work consistently in combat. The integration of so many complex systems is extraordinary. The maintenance implications were equally significant. Japanese bomber crews could field repair their manually operated guns relatively easily. The B-29's remote turret system required specialized training and equipment. Yet American maintenance apparently kept these complex systems operational. Japanese fighter pilots' combat reports suddenly made more sense to the evaluation team. Pilots described attacking B-29s and facing immediate, accurate defensive fire from multiple directions. They reported tracers converging on them from several turrets simultaneously. They described the B-29s as porcupines that were extremely difficult to approach without taking hits. The remote turret system explained these experiences. The B-29 wasn't just defending itself with multiple guns. It was defending itself with a coordinated weapon system that brought multiple guns to bear on threats automatically. This system changes the tactical equation completely, Yamashita wrote in his assessment. Attacking a B-29 means facing computer-coordinated defensive fire from multiple turrets. The defensive firepower is far more effective than simple gun counts suggest. Japanese fighters attacking B-29 formations face casualty rates that make sustained interception operations unsustainable. The psychological impact on Japanese pilots was significant. Knowing that the B-29's defensive system was computer-controlled made it seem almost invincible. Pilots reported feeling that the bombers could see them from all directions and that defensive fire tracked them with uncanny accuracy. The remote turret system represented technology Japan couldn't replicate even if given years to develop it. The electronics, the computing systems, the precision manufacturing of turret mechanisms, all were beyond Japanese industrial capability. After completing the defensive armament analysis, one engineer summarized the situation bluntly. We're fighting an aircraft that has defensive capabilities 10 years more advanced than anything in our inventory. Our pilots are attacking with manually aimed guns while being targeted by computer-controlled weapon systems. The technological gap makes successful attacks extremely difficult regardless of pilot skill or courage. The remote gun turrets were another example of American technology that Japan had no answer for. Like the pressurization system and the turbocharged engines, they represented capabilities Japan couldn't counter, couldn't replicate, and couldn't overcome through tactical innovation alone. The B-29 was revealing itself to be not just a better bomber, but a fundamentally different class of weapon system. Among the recovered B-29 components, Japanese engineers found equipment that initially mystified them. The AN/APQ-13 radar bombing system. Radar technology itself wasn't completely unknown to Japan. Japanese engineers had developed basic radar systems for air defense and naval applications. But they had never seen radar integrated into an aircraft for bombing purposes, and they certainly hadn't seen radar this sophisticated. The AN/APQ-13 was a ground-mapping radar system mounted in the B-29's belly. It could generate images of the terrain below, even through clouds, smoke, or darkness. This meant the B-29 could bomb accurately without ever seeing the target visually. They can bomb through weather, an engineer said, studying the radar components with growing alarm. Cloud cover, which we've relied on for some protection, means nothing to this system. The tactical implications were devastating. Japanese air defenses had used weather as a limited defensive advantage. Heavy clouds could force bombers to abort missions or bomb less accurately. Not the B-29. With radar bombing, clouds were irrelevant. The radar system worked by sending radio waves downward and processing the reflected signals. Different types of terrain reflected differently: water, cities, forests, mountains all had distinctive radar signatures. The bombardier could identify targets on his radar scope and release bombs with precision even in total darkness or complete cloud cover. The Japanese evaluation team had limited ability to test the radar system, but they could examine its construction and understand its principles. The level of electronic sophistication was far beyond Japanese capability. The vacuum tubes alone represent manufacturing technology we struggle to replicate, noted an electronics specialist. These are precision-manufactured components produced in quantity. Our radar tubes fail frequently and require hand selection. The Americans apparently manufacture reliable tubes as standard production items. The radar display scope used a cathode ray tube similar to early television technology. The bombardier viewed a circular display showing radar returns from the ground. He could identify target areas, track the aircraft's approach, and time bomb release with precision. Combined with the Norden bombsight for visual bombing in clear conditions, the B-29 had two independent precision bombing systems. If one failed or conditions prevented its use, the other provided backup. Japanese bombers had simple optical bombsights requiring visual identification of targets. Night bombing was essentially impossible with any accuracy. Bombing through clouds meant dropping blindly and hoping for general area effect. The B-29 could bomb Tokyo at midnight through heavy overcast with reasonable accuracy. Japanese defenses had no effective counter to this capability. The navigation systems were equally sophisticated. The B-29 carried multiple radio navigation aids that allowed precise position determination even over the featureless Pacific Ocean. The LORAN, long-range navigation, system used radio signals from ground stations to triangulate position within a few miles even at distances of over 1,000 miles from land. They can navigate across 2,000 miles of open ocean, arrive over the target within minutes of scheduled time, bomb through clouds using radar, and return to base, Yamashita summarized. Each element of this capability is beyond what we can achieve. Combined, they represent operational effectiveness we have no means to counter. The bombing accuracy achievable with these systems was documented in intelligence reports. B-29 formations regularly placed bombs within a few hundred yards of aim points even through cloud cover. Factory complexes, railroad yards, and port facilities were being systematically destroyed with precision that seemed impossible to Japanese commanders who remembered the relatively inaccurate area bombing of earlier war years. The radar bombing system also included identification friend or foe, IFF, transponders that allowed B-29s to identify each other electronically and avoid friendly fire from escorting fighters. This electronic coordination of large bomber formations was another level of sophistication Japan couldn't match. Japanese engineers examined the electrical power requirements for the radar system. The multiple radar sets, the computing equipment, the display systems, all required significant electrical power that was provided by the B-29's multiple generators without affecting other systems. This aircraft generates more electrical power than many of our factories, an engineer noted. And they need that power to operate all the electronic systems. We couldn't power this equipment even if we could build it. The maintenance and reliability of the radar systems was another revealing factor. American electronics apparently operated reliably under combat conditions with reasonable maintenance intervals. Japanese radar equipment was notoriously unreliable, requiring constant attention and frequent tube replacements. The difference was manufacturing quality and design philosophy. American electronics were designed for operation by trained but not expert technicians. Japanese electronics required specialists for proper maintenance. After examining the radar and bombing systems, the evaluation team added another grim conclusion to their report. The B-29's radar bombing capability eliminates weather as a defensive factor. Night operations, cloud cover, and smoke provide no protection against these bombers. Combined with their high-altitude capability and defensive armament, the B-29 can attack any target in Japan at any time under any weather conditions with reasonable accuracy. We have no effective counter to this capability. One engineer raised a question that had been troubling the entire team. If the Americans have this level of technology in their bombers, what other capabilities might they possess that we haven't yet encountered? It was a question no one could answer. But the B-29 evaluation was revealing that America's technological advantage was broader and deeper than Japanese leadership had understood. Every system examined showed sophistication beyond Japanese capability. The radar bombing system was perhaps the most strategically significant revelation. It meant Japan's cities and industries were vulnerable regardless of weather, time of day, or defensive measures. The B-29 could find targets, bomb accurately, and return to base using technologies Japan couldn't counter or replicate. As one engineer noted in his personal diary, "We are fighting an enemy who can see in the dark, bomb through clouds, and hit targets with precision from altitudes we can barely reach. This is not a matter of courage or determination. This is a technological capability gap that cannot be overcome by fighting spirit alone." The radar systems were another piece of the overwhelming technological superiority the B-29 represented. And Japanese engineers were running out of hope that any countermeasure could be effective. As Japanese engineers disassembled B-29 components for detailed examination, they encountered perhaps the most disturbing revelation of all. The manufacturing quality was extraordinary, and it was clearly the product of mass production, not hand craftsmanship. Every rivet was precisely placed. Every weld was consistent. Every component fit together with minimal adjustment. The B-29 wasn't built by master craftsmen spending weeks on individual aircraft. It was built by factory workers following standardized processes, yet the quality exceeded anything Japanese craftsmen produced. "This is industrial precision at a scale we've never achieved," admitted an engineer from Mitsubishi, examining aluminum skin panels. These panels were stamped from dies, not hand-formed. Yet the dimensional accuracy is perfect. Every panel is identical. The aluminum alloys themselves were superior to Japanese materials. Chemical analysis showed consistent composition throughout different components. The material properties, strength, ductility, corrosion resistance, were uniform and high quality. Japanese aluminum production suffered from inconsistent quality. Alloy composition varied between batches. Material properties were unpredictable. Aircraft manufacturers often had to test and select materials to get adequate performance. "The Americans have standardized their metallurgy to a degree we cannot match," reported the materials specialist. "Every sheet of aluminum meets specifications. There's no variation, no need for selection or testing. This is only possible with sophisticated quality control throughout the entire production chain." The fasteners, bolts, and hardware throughout the B-29 were all standardized. Every bolt was the same thread pitch and dimension as every other bolt of that type. Nuts were interchangeable. Washers were identical. Japanese hardware varied. Different manufacturers used slightly different specifications. Parts from one factory might not fit aircraft from another factory. Maintenance required stocking multiple variants of similar parts. The electrical wiring was color-coded consistently throughout the aircraft. Red wires were always positive power. Black wires were always ground. Other colors indicated specific functions. Any electrician could trace circuits by following the color code, even without detailed diagrams. Japanese aircraft wiring was inconsistent. Different factories used different color schemes. Sometimes the same factory changed colors between production runs. Maintenance required experienced electricians familiar with specific aircraft variants. The engineering team examined manufacturing techniques visible in the recovered components. The precision was evident everywhere. Holes drilled for rivets were exactly positioned. Bends in sheet metal were consistent. Welded joints showed uniform penetration and strength. "This quality is achievable only with specialized tooling and fixtures," explained a manufacturing engineer. "The Americans have invested enormous resources in production equipment. Jigs, dies, drilling fixtures, welding equipment, all designed to produce identical parts repeatedly. We still rely on skilled workers measuring and adjusting each component individually." The cost implications were staggering. The B-29 reportedly cost over $600,000 per aircraft. For that price, Japan could build dozens of fighters. Yet America was producing B-29s by the hundreds, apparently accepting the enormous cost as necessary for the capability provided. They can afford this because their industrial capacity is so much larger than ours, Yamashita noted. What seems impossibly expensive to us is acceptable to them because they're producing everything else they need simultaneously. We must choose between fighters or bombers, between engines or airframes. They build everything at once. The production rate intelligence was almost unbelievable. American factories were reportedly producing over 100 B-29s per month by late 1944, from multiple production lines. Each aircraft required approximately 55,000 man-hours to complete, yet they emerged from factories in a steady stream. Japanese aircraft production was measured in thousands per year for all types combined. The Americans were producing one type of heavy bomber at rates approaching Japan's entire aircraft output. The assembly techniques revealed mass production methods Japan had never implemented. Sub-assemblies were built separately, then mated during final assembly. Wings were built at one facility, fuselages at another, engines at a third. Everything came together at final assembly plants with precision that required minimal adjustment. Japanese aircraft were still largely hand-built from start to finish. Each aircraft was slightly different from the next. Interchangeability of parts between aircraft was limited. Maintenance required fitting and adjusting replacement components to each specific aircraft. The B-29's design itself facilitated production. Components were designed for ease of manufacture and assembly. Complex curves were minimized. Most structures used simple shapes that could be produced with basic tooling. Wherever possible, the design used flat or gently curved surfaces that were easy to form. The Americans didn't design the best aircraft possible, observed a design engineer. They designed the best aircraft that could be mass-produced with available industrial capabilities. That's a fundamentally different approach from our pursuit of optimal performance regardless of production difficulty. The quality control systems were evident in markings found throughout the aircraft. Inspector stamps, date codes, lot numbers, every component was traceable to its source and production date. If problems occurred, the Americans could identify which production batch was affected and take corrective action. Japanese production had minimal traceability. Quality depended on individual inspector judgment. If problems occurred, identifying the source was difficult or impossible. After weeks of examining B-29 construction and manufacturing, the evaluation team reached painful conclusions. Their report stated, the B-29 represents not just advanced aircraft design but advanced manufacturing capability that Japan cannot replicate. The Americans have created an industrial system that produces complex aircraft with consistent quality at rates we cannot match. The precision, standardization, and quality control visible in every component are beyond current Japanese industrial capability. The manufacturing analysis was perhaps more discouraging than the technical findings. Japanese engineers might eventually develop technologies like pressurization or radar bombing. But creating the industrial infrastructure to produce such aircraft in quantity would require years and resources Japan didn't have. One engineer summarized the situation bluntly, "We're not just behind in aircraft design. We're behind in manufacturing capability, quality control, materials science, and industrial organization." The B-29 reveals that American industry operates at a level of sophistication and scale that we fundamentally misunderstood. They don't just have better technology. They have better systems for turning technology into operational weapons at scale. The manufacturing quality of the B-29 proved that America's industrial advantage was even greater than Japan had feared. It wasn't just that they could build more aircraft. They could build vastly more complex aircraft with better quality while also producing everything else their military needed. Japan's industrial capacity was already stretched to the breaking point, producing much simpler equipment. The B-29 proved the contest was never even close. Japanese fighter pilots had been reporting for months that B-29s were extraordinarily difficult to shoot down. Now, examining the recovered components, engineers understood why. The defensive armament system wasn't just about the number of guns. It was about how those guns were employed as an integrated weapon system that turned the B-29 into a nearly impregnable fortress. The 12.50 caliber Browning M2 machine guns represented firepower that could shred attacking fighters. Each gun fired approximately 800 rounds per minute. 12 guns meant 9,600 rounds per minute of defensive fire, 160 rounds per second. An attacking fighter enters a cone of fire that is essentially a metal storm, calculated a weapons specialist. If even a fraction of those rounds hit, the fighter is destroyed. The volume of fire is overwhelming. The Browning M2 itself was a formidable weapon. The .50 caliber round could penetrate light armor, destroy engines, and kill pilots at ranges exceeding 1,000 yards. American ammunition included armor-piercing, incendiary, and tracer rounds mixed in the belts, creating devastating effect on target. Japanese fighters like the Zero and Ki-43 had minimal armor protection and no self-sealing fuel tanks. A few hits from .50 caliber fire could destroy them completely. Even armored fighters like the Ki-61 were vulnerable to sustained .50 caliber fire. The fields of fire were carefully designed. The top forward turret covered attacks from above and ahead. The top rear turret covered above and behind. The two lower turrets covered belly attacks. The tail position covered direct rear approaches. There was no blind spot. Every approach angle was covered by at least two turrets, most by 3 or more. The remote control system meant multiple gunners could concentrate fire on a single attacker. Intelligence reports described instances where 4 or 5 turrets tracked a single fighter simultaneously, pouring hundreds of rounds at it within seconds. The defensive system creates overlapping zones where attacking fighters face fire from multiple directions, Yamashita noted. Even if a pilot evades one turret, he flies into the field of fire of another. The coordination is impossible to counter tactically. The tail position deserved special attention. In addition to twin .50 caliber guns, some B-29 variants carried a 20 mm cannon in the tail. This was specifically to engage fighters making stern attacks, the most common approach angle. The 20 mm cannon had much longer effective range than machine guns. Tail gunners could engage attacking fighters at ranges of 1,500 yards or more, forcing them to maneuver defensively before getting within their own weapons range. Japanese fighter pilots reported that approaching a B-29 from behind meant flying through a gauntlet of fire that started at ranges where their own guns were ineffective and intensified as they closed. Many pilots were shot down before achieving firing position. The ammunition capacity enabled sustained defensive fire. With approximately 6,000 rounds of .50 caliber ammunition, B-29 gunners didn't need to conserve carefully. They could fire sustained bursts at attacking fighters without worrying about running out of ammunition during a 15-hour mission. Japanese fighters typically carried ammunition for 10 to 20 seconds of continuous fire. Pilots had to make their shots count. B-29 gunners could fire for minutes if necessary. The rate of fire was also significant. The Browning M2 at 800 rounds per minute was faster than most Japanese weapons. Combined with 12 guns, the B-29 put more rounds in the air in 5 seconds than many Japanese fighters carried in total. The tracer rounds helped gunners adjust fire. Every fifth round was typically a tracer, creating visible streams of fire that allowed rapid correction. Japanese pilots reported that B-29 defensive fire looked like red streams of light, converging on them from multiple directions. The psychological impact on Japanese pilots was severe. Pilots knew that attacking B-29 formations meant flying into intense defensive fire with high probability of being hit. Many pilots reported fear and hesitation when ordered to attack, which degraded their effectiveness even when they made the attempt. The armor protection for the B-29's gunners was another advantage. The turret positions had armor plating protecting the mechanisms. While the gunners themselves sat in the pressurized compartments away from the guns, the equipment was protected from defensive fire. Japanese fighter weapons struggled to disable B-29 turrets. the 7.7 mm machine guns were ineffective. The 20 mm cannons could damage turrets but required accurate hits on small, distant targets while under fire. Combat reports indicated that B-29s often returned to base with battle damage but still functional defensive systems. The redundancy and robust construction meant losing one or two turrets didn't cripple the defensive armament. The evaluation team studied Japanese fighter tactics against B-29s and found they were largely ineffective. Head-on attacks, traditionally effective against bombers, were suicidal against B-29s due to the forward-firing turret and the combined firepower of formation flying. Side attacks faced fire from both upper and lower turrets. Diving attacks from above were covered by the top turrets. Attacks from below faced the lower turrets. The only approach with any success was high-speed passes from slight angles, but these gave attackers only brief firing opportunities. Our pilots are being asked to attack an aircraft that has no weak points in its defensive coverage, Yamashita concluded. Every approach angle is covered by computer-controlled, remotely operated weapons with overwhelming firepower. The defensive system is nearly perfect from a design standpoint. The comparison to Japanese bomber defensive armament was stark. Japanese bombers typically had 3 to 5 hand-operated machine guns with limited ammunition and no central coordination. Crews were exposed at gun positions. Fields of fire had significant blind spots. Our bombers rely on fighter escort for protection, an engineer noted. The B-29 is designed to fight its way to and from the target without escort. The defensive armament is sufficient to make attacks very costly for interceptors. The casualty rates bore this out. Japanese fighter units attacking B-29 formations suffered losses of 10 to 20% per mission. Such attrition rates were unsustainable. Fighter units were being destroyed faster than they could be replaced, not by American fighters, but by B-29 defensive fire. After completing the defensive armament analysis, the evaluation team added another grim assessment. The B-29's defensive armament system is the most effective we have examined on any aircraft. The combination of firepower, fields of fire, remote control coordination, and ammunition capacity creates a defensive capability that Japanese fighters cannot overcome through tactical skill alone. Attacking B-29 formations results in prohibitive casualties that make sustained interception operations impossible. The fork-tailed devil of the Pacific had 12.50 caliber fangs and wasn't afraid to use them. Japanese fighters were learning this lesson at terrible cost. The strategic implications of the B-29's range and payload capability were perhaps the most devastating aspect of the entire evaluation. The numbers were staggering. Maximum range with a full bomb load, 3,250 miles. Maximum bomb load, 20,000 pounds. With reduced bomb loads, the B-29 could fly over 5,600 miles. Japanese engineers examined maps and calculated distances. From the Mariana Islands, Saipan, Tinian, and Guam, to Tokyo was approximately 1,500 miles. This meant B-29s could fly to Japan, spend time over target fighting through defenses, and return to base with fuel reserves. The round trip was well within the B-29's operational radius. Every city in Japan is within range of B-29s based in the Marianas, Yamashita stated grimly. Tokyo, Osaka, Nagoya, Kobe, all are vulnerable, and we have no way to attack their bases. The strategic asymmetry is total. Japanese bombers, by comparison, had ranges of 1,500 to 2,000 miles maximum. They could not reach the Marianas from Japanese bases. They couldn't reach American bases anywhere. Japanese strategic bombing capability was effectively zero. The bomb load capacity was equally devastating. 20,000 pounds meant the B-29 could carry 4,500-pound bombs or 10 2,000-pound bombs. A formation of 30 B-29s, a typical raid size, could deliver 600,000 pounds of explosives. A larger raid of 100 B-29s could drop 2 million pounds of bombs. Japanese cities, built largely of wood and paper, were catastrophically vulnerable to incendiary bombing. Intelligence reports indicated the Americans were developing new incendiary bombs specifically designed for Japanese urban areas. The combination of B-29 payload capacity and incendiary weapons meant entire cities could be burned. The fuel capacity that enabled such range was itself impressive. The B-29 carried over 9,000 gallons of fuel in wing tanks, fuselage tanks, and optional bomb bay tanks. This was more fuel than most Japanese bombers weighed empty. The fuel management system automatically balanced fuel between tanks to maintain proper center of gravity as fuel was consumed. Pilots didn't need to manually manage fuel transfers constantly. The system handled it, reducing crew workload on missions lasting 15 hours. Japanese engineers calculated the logistics required to support B-29 operations. Each mission consumed 9,000 gallons of fuel per aircraft. A 100-plane raid required 900,000 gallons of fuel. The Americans apparently had no difficulty supplying this fuel to forward bases in the Pacific, despite the enormous distances involved. Their logistics capability is as impressive as their technology, noted an intelligence analyst. They can sustain operations at the end of a 6,000-mile supply line that would overwhelm our logistics entirely. The fuel alone for one B-29 raid exceeds what we can move to forward bases in a month. The payload flexibility was another advantage. The B-29 could be configured for different mission types by changing the bomb load. High explosive bombs for industrial targets. Incendiaries for cities. Mines for harbors. The aircraft was a versatile weapon system, not just a single-purpose bomber. The bomb bay was designed for rapid loading. Ground crews could load 20,000 pounds of ordnance in under an hour with proper equipment. The Americans had developed specialized bomb loading equipment that made the process efficient even in field conditions. Japanese bombers required hours to load much smaller bomb loads. The process was manual and labor-intensive. Quick turnaround for multiple missions per day was impossible. The operational tempo the B-29's range enabled was strategically decisive. A base in the Marianas could launch raids against Japan, recover, rearm, and launch again within 24 hours. The B-29 force could maintain continuous pressure on Japanese targets without pause. They can bomb us daily, or even multiple times per day if they choose, Yamashita observed. We have no equivalent capability to strike back. We're in a strategic bombing campaign where only one side can reach the other's homeland. The range also provided operational flexibility. If weather was bad over Tokyo, B-29s could divert to secondary targets in Osaka or Nagoya without approaching fuel limitations. If primary targets were obscured, they could search for targets of opportunity and still return safely. Japanese bombers had no such flexibility. Missions were carefully planned with minimal reserves. Any deviation from plan, weather, combat damage, navigation errors, meant aircraft running out of fuel and being lost. The evaluation team studied intelligence on B-29 base development in the Marianas. The Americans had constructed massive air bases with long runways, hardened revetments, fuel storage for millions of gallons, and bomb storage for tens of thousands of tons of ordnance. These bases could support hundreds of B-29s operating continuously. The infrastructure investment is staggering, noted an engineer. They've built bases in the middle of the Pacific Ocean that are larger than our main air bases in Japan. The construction equipment, materials, and labor required to do this while simultaneously fighting the war demonstrates industrial capacity beyond our comprehension. The range payload combination had another implication. The B-29 could reach targets deep in China, Manchuria, Korea, and throughout the Pacific. No Japanese installation was safe. Factories in Manchuria, ports in Korea, military facilities throughout occupied territories, all were vulnerable. The strategic bombing capability the B-29 provided fundamentally changed the Pacific War. Japan could not defend everywhere simultaneously. Air defenses concentrated around Tokyo meant other cities were vulnerable. Defenses spread evenly meant nowhere had adequate protection. We face an impossible defensive problem, Yamashita wrote in his assessment. We cannot prevent B-29 attacks on any target they choose. We can attempt to make attacks costly, but we cannot stop them. The strategic initiative is entirely theirs. After documenting the range and payload capabilities, the evaluation team added a stark conclusion. The B-29's range and payload capacity provide America with strategic bombing capability that Japan cannot counter or reciprocate. Every target in Japan and occupied territories is vulnerable to precision bombing at times of American choosing. Japan's inability to strike American bases or homeland creates total strategic asymmetry. The B-29 makes defeat inevitable unless some counter can be developed. No such counter appears possible with available Japanese technology and resources. The range of the B-29 meant Japan's cities, factories, ports, and people were hostages to American air power. And there was nothing Japan could do to change that reality. By early January 1945, the B-29 evaluation at Tachikawa Air Arsenal was complete. Colonel Takeo Yamashita faced the difficult task of writing a comprehensive report that would go to the highest levels of Japanese military command. The report would not be well received. Everything the evaluation revealed pointed to the same conclusion. Japan had no effective defense against the B-29 Superfortress, and developing one was beyond Japanese capability. Yamashita gathered his senior engineers for a final assessment meeting before writing the report. The mood was somber. "Gentlemen, we must be honest in our conclusions," Yamashita began. "Lives depend on accurate information reaching commanders who must make strategic decisions. What can we definitively state about the B-29 and Japan's ability to counter it?" The responses came systematically, area by area. The pressurization system allows the B-29 to operate at altitudes where Japanese fighters are barely effective. We cannot replicate this technology with current capabilities. The turbocharged engines provide power and high-altitude performance we cannot match. Our best fighters struggle at 30,000 feet while the B-29 operates comfortably. The remote-controlled defensive armament creates a weapon system we have no equivalent for. Attacking B-29s results in prohibitive casualties. The radar bombing system makes weather irrelevant. We cannot hide targets under clouds or conduct operations at night without being vulnerable. The range and payload capability means every location in Japan is within striking distance, and we cannot retaliate against American bases. The manufacturing quality demonstrates industrial capacity we cannot compete with. They're producing these complex aircraft in quantities that overwhelm any tactical advantages we might achieve. Yamashita listened to each assessment, making notes. The conclusion was inescapable. The B-29 represented technological and industrial superiority that Japan could not overcome. The report took 3 days to write. Yamashita chose his words carefully, knowing that stating unpleasant truths could be dangerous in Japan's military hierarchy where optimism was often valued over realism. The executive summary was direct. The B-29 Superfortress represents aviation technology approximately 10 years more advanced than current Japanese capabilities. Key systems including pressurization, turbocharged engines, remote-controlled defensive armament, and radar bombing provide operational capabilities for which no effective Japanese counter exists. Current Japanese fighters and defensive measures are inadequate to prevent B-29 raids. Developing equivalent Japanese capabilities would require technological advances and industrial infrastructure beyond current resources. The recommendations section was more difficult to write. Yamashita knew he had to provide something actionable, even though the situation was nearly hopeless. Immediate recommendations: concentrate defensive fighters around critical industrial targets rather than attempting area defense. Accept that many targets will be hit without opposition to maximize defensive effectiveness at priority locations. Develop specialized high-altitude interceptors sacrificing all other performance characteristics for altitude capability. Existing fighters cannot effectively engage B-29s at operational altitudes. Increase anti-aircraft artillery defenses around major cities. While AAA cannot stop raids, it can increase B-29 losses and potentially force raids to higher altitudes where bombing accuracy decreases. Implement aggressive dispersal of critical industries. Concentration of manufacturing makes it vulnerable to precision bombing. Dispersed facilities are harder to destroy completely, though less efficient to operate. Accept that strategic bombing will continue and cannot be stopped. Focus defensive resources on minimizing damage rather than preventing raids entirely. The final section addressed the question of developing Japanese capabilities to counter or match the B-29. Yamashita was blunt. Japan cannot develop equivalent aircraft capabilities within any time frame relevant to the current conflict. The technological gaps in engines, electronics, pressurization, and fire control systems represent years of development even under optimal conditions. Current resource constraints and industrial degradation make such development programs unrealistic. Japan must accept technological inferiority in strategic bombing and focus available resources on tactical operations where technological advantages are less decisive. The report was completed on January 8, 1945. It was classified Most Secret and distributed to a limited group of senior commanders and staff officers. The response was varied. Some commanders accepted the findings and began implementing dispersal and defensive concentration as recommended. Others rejected the conclusions as defeatist, insisting that Japanese fighting spirit could overcome American technological advantages. High command faced an impossible situation. The B-29 evaluation confirmed what battlefield experience already suggested. Japan was losing the air war and had no means to reverse the situation. But accepting this meant accepting that defeat was inevitable unless some dramatic change occurred. Some commanders seized on the kamikaze tactic as a potential answer. If conventional attacks were too costly and ineffective, perhaps suicide attacks could achieve better results. The desperation of this logic indicated how hopeless the situation had become. Intelligence reports in early 1945 confirmed Japanese fears. B-29 production was accelerating. More bomber groups were deploying to the Marianas. Raids were increasing in size and frequency. And American industry was developing even more devastating incendiary weapons specifically for Japanese cities. On the night of March 9 to 10, 1945, 2 months after the evaluation report was completed, 334 B-29s attacked Tokyo with incendiary bombs. The resulting firestorm killed over 100,000 people and destroyed 16 square miles of the city. It was the single most destructive air raid in history to that point. Similar raids followed against other major cities. Osaka, Nagoya, Kobe, Yokohama, each was systematically burned. Japanese air defenses, already inadequate, were overwhelmed. B-29 losses were low, typically under 3% per mission. The evaluation had predicted this outcome. The B-29's capabilities made such raids inevitable. Japanese defenses couldn't prevent them, couldn't stop them, couldn't even make them too costly to sustain. By summer 1945, Japan's industrial capacity was shattered, its major cities were burned, and its population was demoralized. The strategic bombing campaign the B-29 made possible had achieved its objectives. Japan's ability to sustain the war was collapsing. In August 1945, 2 B-29s, Enola Gay and Boxcar, dropped atomic bombs on Hiroshima and Nagasaki. The ultimate expression of the B-29's strategic capability was delivering weapons so devastating that they ended the war within days. Colonel Yamashita's evaluation report had been accurate and prescient. The B-29 represented capabilities Japan couldn't counter. The technological gap was too wide to bridge. The industrial imbalance was too great to overcome. And the strategic vulnerability it created was absolute. Japan had learned the truth about the B-29 Superfortress. But learning the truth changed nothing. The fork-tailed devil of the Pacific had become the instrument of Japan's defeat, and there was nothing Japan could do to stop it. The B-29 Superfortress evaluation at Tachikawa Air Arsenal ended in early January 1945, but the aircraft's impact on history was just beginning to reach its terrible crescendo. Over the following 8 months, B-29s would prove every capability Japanese engineers had documented. They would bomb from altitudes Japanese fighters could barely reach. They would attack through weather that made visual bombing impossible, using radar to find targets. They would defend themselves with computer-controlled guns that destroyed attacking fighters. They would fly thousands of miles carrying tons of bombs, then return safely to bases Japan couldn't touch. The statistics tell the story of the B-29's effectiveness. Between June 1944 and August 1945, B-29s flew over 31,000 combat sorties. They dropped 171,000 tons of bombs on Japanese targets. They destroyed or damaged over 600 square miles of urban area. The strategic bombing campaign they enabled killed hundreds of thousands of Japanese civilians and crippled Japan's industrial capacity. B-29 losses, while significant in absolute numbers, were sustainable. Approximately 414 B-29s were lost in combat operations, roughly 1.3% loss rate per sortie. Japanese defenses could harass the bombers but couldn't stop the raids or make them prohibitively costly. The B-29's most significant missions came in August 1945. On August 6, the B-29 Enola Gay dropped the atomic bomb on Hiroshima. 3 days later, Bockscar dropped a second atomic bomb on Nagasaki. These missions, impossible for any aircraft except the B-29, effectively ended World War II. The aircraft that Japanese engineers had examined so carefully at Tachikawa had become the instrument of Japan's surrender. Everything the evaluation predicted came true. Japan couldn't defend against it, couldn't replicate it, couldn't counter it. The B-29 evaluation report itself survived the war. American intelligence officers found it among captured Japanese documents in 1945. Reading it, they recognized that Japanese engineers had understood the B-29's capabilities accurately and had correctly assessed that Japan had no effective defense. Colonel Yamashita survived the war, though his fate afterward is unclear. Many of the engineers who worked on the evaluation returned to civilian life and helped rebuild Japan's aircraft industry in the post-war years. The Soviet Union's acquisition of B-29s interned in their territory led to one of history's most significant technology transfers. Soviet engineers, led by Andrei Tupolev, reverse-engineered the B-29 completely. The result was the Tupolev Tu-4, virtually identical to the B-29. The Soviets copied everything, down to minor manufacturing flaws they found in the original aircraft. The Tu-4 gave the Soviet Union strategic bombing capability years sooner than their own development programs would have achieved. It was the Soviet Union's primary nuclear-capable bomber in the late 1940s and early 1950s. The B-29 design, copied by necessity, became a cornerstone of Soviet air power during the early Cold War. For the United States, the B-29 validated strategic bombing as a war-winning capability. It led to continued investment in strategic bomber development, resulting in the B-36, B-47, and eventually the B-52, which remains in service today, 80 years after the B-29's first flight. The technologies pioneered or perfected in the B-29, pressurization, remote-controlled systems, radar bombing, central fire control, became standard features of military and civilian aircraft. Modern airliners owe their pressurized comfort to technology first deployed operationally in the B-29. For Japan, the B-29 experience influenced post-war thinking profoundly. Japanese engineers who examined the Superfortress understood that war had become technological and industrial. The martial spirit that Japanese military culture emphasized so strongly had proven insufficient against technological superiority. Post-war Japan focused on technological development and industrial capability with an intensity partly born from the bitter lessons of defeat. The nation that couldn't match American manufacturing in 1945 became an industrial powerhouse by the 1970s, applying lessons learned partially from examining aircraft like the B-29. The B-29 evaluation revealed truths that extended beyond aviation technology. It demonstrated that industrial capacity, technological sophistication, and systematic quality control could create decisive military advantages. It showed that producing adequate equipment in overwhelming numbers could defeat theoretically superior equipment available in limited quantities. These lessons influenced Cold War military thinking on both sides. The Soviets emphasized mass production of adequate equipment. The Americans balanced quantity with continued technological advancement. Both approaches traced partly to lessons learned from the B-29 experience. Today, only a handful of B-29s remain airworthy. Fifi and Doc fly occasionally at air shows. Their foreright are 3350 engines producing the distinctive sound that once meant terror for Japanese cities. These survivors are maintained by dedicated volunteers who preserve flying history. For those who lived through the B-29 raids, the memory never faded. Japanese survivors of the firebombing raids remembered the sound of the engines, the sight of incendiaries falling like rain, the firestorms that consumed cities. The B-29 remained a symbol of vulnerability and technological inferiority. The Tachikawa evaluation predicted all of this. Japanese engineers understood what was coming. They documented the capabilities that made it inevitable. But understanding didn't provide solutions. Knowledge without the means to act on it is merely painful awareness of coming defeat. The B-29 Superfortress was more than just a bomber. It was a demonstration of American industrial and technological power. It was a weapon system so advanced that enemies couldn't counter it or copy it. It was the instrument that ended the Pacific War and shaped the post-war world. Japanese engineers who examined the B-29 in late 1944 understood they were seeing the future of warfare. A future where technology and industry mattered more than courage or fighting spirit. A future where Japan had fallen behind and had no path to catch up. The evaluation report Colonel Yamashita wrote was accurate, honest, and ultimately ignored by commanders who preferred comforting myths to uncomfortable truths. By the time reality forced acceptance of those truths, Japan's cities were burning and defeat was inevitable. The B-29 had done what it was designed to do. It had brought strategic bombing to Japan with precision and devastation that proved unstoppable. It had demonstrated American superiority in aviation technology, manufacturing capability, and industrial warfighting in ways that left no room for doubt. For the Japanese engineers who examined it piece by piece, system by system, the B-29 revealed a truth they couldn't escape. They were facing an enemy whose technological and industrial advantages were insurmountable. And that realization, more than any single battle or campaign, marked the moment when Japan's defeat became inevitable. The fork-tailed devil of the Pacific had shown them the future. And in that future, there was no place for Imperial Japan except surrender.